Our next presentation is about repair methods. These are the first presentation about repair methods. It's about realkalisation and chloride extraction and desalination. This presentation will be made by Koichi Kobayashi. Koichi is the Deputy Director of the Center for Infrastructure and Asset Management Technology and Research at the Gifu University in Japan since 2014. He was also the Secretary General of the Concrete Committee of the Japanese Society of Civil Engineering. So, Koichi, as soon as possible, you can start your presentation.
I'd like to lecture on realkalisation and chloride extraction. It's also called.
Are you listening?
As
yes, now it's okay.
In the Bulletin, realkalisation is in chapter 6 and chloride extraction is in chapter 7. These two repair methods are very similar to each other. Therefore, we decided to explain by combining them together. First, I begin with realkalisation. It's an electrochemical method used for the repair of reinforced concrete that is subjected to carbonation. The aim of this method is to prevent reinforcement corrosion by increasing the alkalinity of concrete. In other words, increasing the pH value of concrete. This diagram illustrates the principle of realkalisation. A direct current is supplied by DC source and applied between a temporary metal anode set on the concrete surface and rebar in the concrete member. Typically, a direct current of less than 5 amperes per square meter of rebar surface or 1 to 2 ampere per square meter of concrete surface is applied for 1 to 2 weeks. Carbonate in the electrolyte supplied on the concrete surface migrates inside by the electrophoresis. Generally, sodium carbonate, potassium carbonate, or lithium carbonate is used here. Another role of electrolytes is to ensure the resistivity between concrete and the anode to make the migration easier. After the application of realkalisation, the buffer of carbonate and bicarbonate, whose pH is around 10.4, is generated around rebar as shown in this formula. As far as this situation is maintained, no recarbonation of copper concrete, no redepassivation of rebar breaks out. Next one is chloride extraction. This is also an electrochemical repair technique, but it is applied for extracting chloride ions from concrete structures that suffer chloride attack. The aim of this treatment is to extract the chloride ions from the concrete cover by electrophoresis, and therefore to decrease or stop the corrosion of rebar. As you can see in this diagram, the principle of chloride extraction is very similar to that of realkalisation. A direct current is supplied by DC source and applied between a temporary metal anode set on the concrete surface and the rebar in the concrete member. Typically, a direct current of less than 5 ampere per square meter of rebar surface or 1 to 2. ampere per square meter of concrete surface is applied for 8 weeks. That is longer than realkalization. Chloride in the concrete moves from inside towards an anode by electrophoresis. In this technique, saturated solution of calcium hydroxide is most widely used as an electrolyte to maintain alkalinity and avoid acid attack. Another role of electrolyte is to ensure the resistivity between concrete and anode to make the migration easy. This table compares the characteristics of 3 electrochemical repair methods. As you can see, the most evident difference between cathodic protection and realkalization and chloride extraction is their execution times. In the case of cathodic protection, it must be being applied until the end of the service life of the structure. In contrast, the other 2 methods can be finished within a few weeks or months. Another difference is the application current. Those for the realkalization and chloride extraction are 100 times larger than that for cathodic protection. The method for the quality control is explained later in this lecture. Here, an example of the application of realkalization to the historic building. This is a theater built in 1930 to celebrate the marriage of emperor. This building suffered river corrosion and cover spalling caused by carbonation. By considering its historic value, municipal government decided to preserve this building by applying realkalization. In the left bottom picture, you can see the temporary metal anode with a mesh shape and electric wires connected to the reinforcing bar. The right bottom picture shows the electrolyte retainer sprayed on the anode. The mesh anode is completely covered by the electrolyte retainer. This is a close-up of the electrolyte retainer. I cannot say that this wire is connected to the reinforcing bar or mesh anode. However, usually it can be distinguished by the color. In this repair, as an electrolyte retainer, cellulose fiber was employed. It was sprayed on the surface of the concrete and mesh anode. This is DC power supply and switch boxes. And you can see that potassium carbonate was used as an electrolyte. Point of attention for both realkalization and chloride extraction are as below. If the sufficient amount of oxygen is not supplied due to too rapid reaction by too large voltage or too large current flow, it causes hydrogen gas generation due to this reaction. It causes the crack generation in cover concrete and hydrogen enrichment of PC tendons. Later, as case study 4 of this lecture, an example of the chloride extraction applied to the pre-stressed concrete bridge will be presented. One more important thing is that alkali will be accumulated around the reinforcing bar. This may cause acyl reaction if reactive aggregates are present in the concrete member. In such a case, lithium hydroxide or lithium carbonate should be used as an electrolyte to suppress the formation of expansion gel. Points of attention peculiar to chloride extraction are as below. As the chloride travels due to the potential difference between anode and reinforcing bar, chloride that has penetrated deeper than the river cannot be removed sufficiently. If the structure contains a large amount of chloride beyond the river, other methods, such as permanent cathodic protection, need to be employed. Principal materials and systems are shown in this page. First one is electrolyte solution that has already been explained. The next one is anode method to prevent electrolytic corrosion. Mixed metal oxide coated titanium, noble metal coated alloy, stainless steel, and so on shall be used. This is applied with a sufficient capacity. And electrolyte retainer that is used for retaining the electrolyte solution on a concrete surface during the treatment must be selected. Electrolyte retainer is used to make the electrolyte solution saturate sufficiently between the anode on the concrete surface and the river. First one is cellulose fiber layer. It is sprayed on the concrete surface to cover the anode metal. Its advantage is that it can be used for complex structure surfaces. The drawback is easy escape of electrolyte solution through evaporation and leakage. However, it can be removed easily after the execution. This is a panel type retainer. It is set on the concrete surface to form a closed space filled with the electrolyte solution. While capable of retaining electrolyte solution well, panels can hardly be adopted for complex shaped surfaces. The last one is ponding. Ponding of electrolyte solution on a concrete surface can be achieved simply, although only applicable on slabs. Also, electrolyte retention is poor, so the electrolyte can easily evaporate. In the following a few pages, it is explained the design of realkalisation and chloride extraction. First of all, the conditions of concrete structures must be investigated. Carbonation depth and chloride distribution are the most important information for realkalisation and chloride extraction, respectively. Index profile of chloride penetration from the surface to the backside of the river is required. Conditions of cover concrete must be checked as it affects the electric current distribution greatly. The river arrangement must be specified for the circuit design, such as connection points between the river and the red wires, the number of connections, the DC power supply capacity, the number of power supplies, and so on. In addition, the presence of braceless tendons must be checked. Environment is an important factor as it affects the redeterioration after the treatment. Pre-treatment is very important to secure the even current distribution. So, damaged concrete and reinforcement must be repaired. All the spalling, falling, cracks, and other defects must be repaired beforehand. The repair materials shall have a necessary strength. However, polymetric concrete or mortars shall not be used as its electric resistivity is too high. The cracks must be sealed by the crack sealers. The next step is to set a target carbonation depth or a target chloride amount or chloride profile. Then, the arrangement of anode has to be decided, specifically anode metal layout and the type of electrolyte retainer. In the case of chloride extraction, rediffusion of chloride after the execution must be calculated. Generally, an electric current of 1 ampere per square meter of steel surface or 1 ampere per square meter of concrete surface is applied. They are applied for 1 to 2 weeks in the case of realkalization and 8 weeks for chloride extraction. The current density and application period must be decided based on the river permeability of concrete, cover depth, and carbonation depth or chloride distribution. Excess current, for example, 10 ampere or more per square meter of concrete surface can cause significant cracks. DC power supply must have sufficient capacity. If it is expected that the structure will be exposed to chloride and that the chloride amount around the river may increase during the remaining service life of the structure, coating material shall be selected appropriately by considering the high humidity and high alkalinity of the concrete surface due to the electrolyte. The surface coating is also effective to maintain the carbonate in the concrete after the application of realkalization, even when the concrete surface is exposed to the rainfalls. The maintenance plan must be prepared beforehand. The next is the execution process. At first, we have to conduct preparatory works. To provide even current distribution, surface coating and deteriorated concrete must be removed. Cracks must be sealed and patched. If the reinforcement is damaged, it must be restored. Metal parts such as the bolt and the separator in cover concrete must be found by using a river detector and be removed because they can cause short circuiting. Metal objects within the execution area, such as guardrails, water pipes, and so on, shall be temporarily welded to the river or shall be temporarily removed or shall be separated from the anode by more than 20 centimeters to avoid electrolytic corrosion. The next step is the execution itself. In connecting river to DC power, exact locations of river shall be determined by using a non-destructive method. An appropriate number of connection points between lead wires and the river shall be determined based on the current capacity of the lead wire and the diameter of the river. Then, the anode is installed on the concrete surface. The anode metal is set several centimeters apart from the concrete surface. You can see that wood beams are used as spacers between the concrete and the anode mesh. An electrolyte retainer is set over the anode, and the electrolyte solution is supplied. The amount of electrolyte is determined in consideration of expected loss caused by absorption into concrete and evaporation into the surrounding air. Finally, the wires from the anode and those from the river are connected to the DC power supply. Then, the electric current is applied with the designed strength. After finishing current application, the entire anode system is dismantled. Drilled holes and core boring holes must be filled. As a quality control measure before the execution, it is necessary to check the connection among all the rivers to achieve a uniform electric current flow. Quality control on the current flow during the execution is very important. The electric current will vary to some extent, since the cover depth, amount, and arrangement of river in the RC member are not uniform. However, if the current variation exceeds plus minus 30%, it can indicate a connection failure or an electrical short circuit. Large increase of the voltage may be caused by the disconnection in the wire or a lack of electrolyte. Current and voltage shall be checked not only at the start of current application, but also after the electrolyte has penetrated well into the concrete. The concrete surface shall be checked if it is wet with the electrolyte at least once a week during the execution process. The alkalinity shall also be checked frequently so that it does not fall below pH 10 to avoid generation of chlorine gas. Of course, the DC power supply, anode metal, electrolyte, and lead wire shall be checked regularly. After the execution, carbonation depth or chloride distribution must be investigated in order to check if the designated repair was achieved. This page describes the key points of maintenance that must be carried out after the execution of repair. The structure that underwent realkalization or chloride extraction must be regularly inspected. The most basic item is a visual inspection. New cracks, corrosion stains, new spalling must be checked periodically. Both realkalization and chloride extraction relate to the river corrosion. Therefore, house cell potential of the river gives us significant information that indicates the redeterioration. It should be noted that after the execution of these electrochemical methods, it takes several months to return to its intrinsic true house cell potential. Preferably, the carbonation depth or chloride distribution shall be investigated every several to 10 years. The available codes and standards that relate to these two electrochemical methods are listed here in this page. I introduce 4 case studies. The first one is the realkalization of a historic building. Actually, it is not a castle during the Shogun era, as we have not invented reinforced concrete at the time. The original one burned out by fire, and it was rebuilt in 1931 with reinforced concrete. But it's still important and has historic value. So non-disruptive repair was preferred and realkalization was applied to the entire castle. The average carbonation depth was about 30 millimeter with a maximum of 67 millimeter, while the average cover depth was 50 millimeter. Severe scoring or significant cross-sectional loss of river were not observed. After the patch repair to the slight spoiled area, metal mesh was set as a temporary anode. Then cellulose fiber saturated with a sodium carbonate solution was sprayed thereon. A direct current of 1 ampere per unit concrete surface was applied for 7 days with a maximum voltage of 40 volts. It can be seen from the graph that the carbonation depth reached 0 millimeter on the 5th day. After 25 years since the intervention, the building shows no sign of corrosion or concrete spoil. The next case study is the realkalization of the bridge. Camille de Hobbs Bridge, 150 meter long and 8 meter wide, consisting of 3 beautiful arches, was built at the end of the 19th century. It is one of the oldest reinforced concrete bridges in France. Its cover depth was 50 millimeter, and compressed strength was very low, so it was severely damaged. In addition, no deck proofing was given. Due to an irregular arrangement of bars and cages, a connection to the rivers had to be made every 1 square meter as a minimum. A steel anode, 3 meter in diameter and 5 by 5 centimeter mesh was embedded in a cellulose pulp soaked with a potassium carbonate solution. Current density of 1 ampere per square meter of steel was applied over a 15 days period. After the realkalization treatment, its efficiency was followed for 1 year according to phenolphthalein coloring, potential mappings, resistivity mappings, and corrosion rate measurements. The third case study is on chloride extraction applied for school building. This building was partially but severely damaged by chloride attack. In some of the areas, due to severe cross-section loss, reinforcement had to be reinstalled through the replacement of corroded rebars with new ones. As a preliminary test, the electric continuity of the reinforcement and the chloride content in control areas were checked and evaluated. The anode, consisting of a welded steel mesh, was set between felt layers. In order to enable proper moisturizing of the anode supporting felt layers, a watering system was employed here. This ensures the uniform current distribution. After being tested to ensure the absence of short circuits between anode and cathode, electric current was applied and monitoring of system operation was started. Applied current density was 1 ampere per square meter of steel reinforcement. The anodic system was divided into several blocks. Duration of treatment in each block varied between 4 and 7 weeks. For example, for block A3, it was 3 weeks, while for block A2, it was 6 weeks. The treatment was completed when a reduction of chloride concentration at river to values below 0.4% of cement weight, or minimum 600 ampere hour per square meter of steel surface. As you can see in these graphs, the chloride in concrete was removed appropriately. The last case study is on the chloride extraction of pressless concrete bridge. As I already explained, in the case of PC tendon, the hydrogen enrichment by electric current is concerned. In some parts, chloride amount was roughly 0.5% versus unit cement mass near the reinforcement steel, while the concrete surface did not show any serious damage such as crack, delamination, and spalling. Rebar was exposed at 2 or more locations per 30 square meters of concrete surface, and lead wires were connected. Stainless mesh was fixed on the concrete surface as an anode, and cellulose fiber was spread on them. Current was applied intermittently in a cycle of 5 days on and 2 days off to prevent hydrogen enrichment failures of the PC tendon and deterioration of the bond between the tendon and the concrete. As you can see from this graph, the chloride amount around the river has dropped below the target value of 1.2 kilogram per cubic meter of concrete volume. It's roughly 0.3% of cement weight after 40 days of treatment. It was calculated that the chloride amount will not exceed this value again by the rediffusion after 100 years. The surface coating was investigated periodically. After 10 years, no change has been observed in the structure, including the surface coating. This is the end of my lecture. Thank you for listening patiently to my full English explanation. Thank you.
Thank you very much, Koichi, for this very interesting presentation about 2 methods. Eduardo, there are questions.
Yes, we have a question from the audience. Koichi, please, I don't know if you want to unmute yourself or if you want to turn off the video. The question was from Boris Treiher, and he wanted to know if any of the described process have noticeable impact on the concrete compressive and tensile strength and are on the bond strength. Koichi, I don't know if you want to.
As far as I know, the effect of on the strength is negligible. But however, due to the alkali accumulation along the river, the bond strength between the river and the concrete decreases.
Okay. Thank you, Koichi.
Yeah.
I think we have one more question here from the audience. Sorry, I think it's from Sukdiyo Karade. He says, at chloride content of 9 kilos per cubic meter, the structure might have structurally deteriorated. What did you do?
Yeah, I think it's too high value for the chloride extraction, I think. So I recommend to apply a cathodic protection. I don't think that the chloride extraction can remove the such a large amount of chloride. So yeah, I recommend for such a case cathodic protection.
Okay.
Okay.
Well, I think we don't have any more questions from the audience. I don't know if anyone, we are still on time, so I don't know if anyone wants to put additional question.
There is another. No, it's
No. It's
okay.
Sukriyo thanking for the Koichi answering his question. Maybe I have just I think it's a more a curiosity. I saw when comparing these methods with the cathodic protection, I saw the currents you have to apply are much higher. You said about up to 5 amps per square meter and voltage up to 50 volts.
Yeah.
My question was if there are any safety concerns when applying these methods, or if these high currents and voltage are a disadvantage when selecting these methods.
You mean if the much more voltage is applied, what happens?
Yeah, if it is danger when applying.
Yeah. It may causes hydrogen enrichment of the river, and it may cause it generates the hydrogen gas. So of course theoretically, if we apply very high voltage, it can extract chloride very quickly, but it may cause very harmful effect on the structures. So the appropriate voltage and the appropriate current amount must be selected. Okay, is it the answer for your question?
I saw that on the presentation. I was talking about when applying for the staff and the contractor that are applying this method, if there are any safety concerns, because maybe we need too powerful power supplies. I don't know.
Yeah.
Can you comment on that?
Yeah, you are right. Yeah.
Okay. Well, I think we finished our presentations for the morning.